Good afternoon, everyone. Thank you so much for joining us. I think I just saw we've got Martha with us from California. If my math is correct, it might still be the morning out that way. Thank you so much, each and every one of you, for joining us for our webinar. Another one of our summer, now quickly approaching the fall, Next Wave STEM support webinars, especially since we have been in unprecedented times. We wanted to make sure that we could give as much support as we could to our educators out there. Today, we will be focusing on a very interesting, really exciting topic, using emerging technologies to support next generation science standards. A lot of us have had some robust experience with NGSS for a number of years. In many of our really core curricular areas, when we think about science instruction, have been trending towards Common Core math, and the ability now to pull in next generation science standards will create really, really robust experiences. So it's going to be an exciting thing to think about ways in which we can support our students using technologies that they may have never used before, that you may have used only a little bit or might be completely new to yourself as well. It is a extremely rich opportunity, and I'm glad to share that with everyone today. Before we press forward, there are a couple of housekeeping things that I will most likely remind you about once we reach the end of our webinar today. The first is PD credit hours for our Illinois educators. We love all of our educators, but we are based in Illinois, and that means as of right now, we are only offering credit hours that can be redeemed with Illinois State Board of Education. Their certificate to share and claim that PD time with us today will be sent out after the webinar today. But if you're out of state and just want proof of your attendance for professional development, you will also be receiving that form as well. That's the first thing. The second thing is that we are in webinar mode today. That means that as much as we would love to see and hear from you live, we know that your camera ready, pearly whites have been shined up. Unfortunately, the cameras and mics are closed, but there is an opportunity for you to make yourself heard. So that means that the chat is open. So is the Q&A functionality in Zoom. If you've got any questions about anything, literally anything that we're going to talk about today or about Next Wave STEM, feel free to drop that in the chat. We will make sure to get those questions answered live on air as well. I think that is all of our housekeeping information. So I will go ahead and just introduce myself once again. My name is Desmond Martin. I'm the program coordinator for Next Wave STEM. That means that I have my hands in a bunch of different pots, including curricula development, teacher and instructor training, also with being direct liaison to our schools in the professional development space as well. My formal background is in mechanical engineering, and I'm also really fortunate to have worked in the classroom for a number of years, a little less than 10 years before I started with Next Wave STEM. So really, really great to be here, really great to have you, and really great to jump into the topic, which is where we will begin right now. So Next Wave STEM, we are a new-ish company. Next Wave STEM is a startup focused in educational technology. We are now in year 3. We were founded in 2017. And without focusing too much with what's on the slide deck, Next Wave STEM believes the future lies in the hands of our young people, that future is going to be a future that benefits all of us. There are massive problems that we're facing right now, particularly, but before we had a global pandemic to worry about, we had issues of climate change and food insecurity and issues even here in the United States of potable drinking water. Lots of these problems are going to require big solutions, but more than just big solutions, they're going to require technical resources, STEM solutions. And we know that our children are clever enough to develop and implement some of these resources that our world desperately needs. But they can't do that unless they learn the technology. And they can't learn the technology without you as an educator. We recognize that educators are the most important part of the process. So we imagine ourselves as being a conduit for that empowerment. We want to empower you as educators with our emerging technology curricula, K through 12, and subjects like drones and robotics and 3D printing and even AI. Our courses right now are introductory. They're designed to get you familiar with the technology and then build familiarity with our students as we continue to grow together. But as you grow, we want to create students who feel that they belong in STEM. They're not afraid to get it wrong because they can recover and excel. They can see themselves working in the spaces, and then we see STEM outcomes later on. More students who are enrolled in educational institutions with STEM degrees and a STEM focus, becoming engineers, technologists, mathematicians, artists, and scientists. And using those skills will help literally save the world. Our end goal is kind of lofty, but we want to begin with you as the educator. So thanks again. I'm going to be saying thank you a lot for the continuing work that you're doing, the adjustments that you're making, the ability to continue to be learners yourselves. You're modeling what we need to see from our students and making a huge difference in the history of the entire world. Um, as a child of educators, as an educator myself, I am grateful for each and every one of you. So now that, for lack of better words, we have that out of the way, we have one primary goal for today's webinar. Straight to the point, getting not too far into the weeds, but we want to talk a little bit about the standards. For a lot of us who are transitioning now to hybrid learning models for the fall, and maybe there for the foreseeable future, many of us recognize also that those learning models might change. We don't know exactly what will happen with regards to transmission, to regards with vaccine, to regards resurgence. Living in a future that we don't know, the best that we can do is prepare for as many circumstances as we can. And with that in mind, it is helpful to think about developing experiences that align to the NGSS, even knowing that where we were going to sit with assessment is kind of up in the air in a bunch of different situations and scenarios. We still want to create experiences that align with NGSS because of what the NGSS is and what it does, and also in the ways that we can really cleverly leverage some emerging technologies to do that. So I'm really hopeful that we get a chance to take a look at some examples of emerging technologies, take a look at some specific standards, then talk about the experiences that we can align using those technologies, while also throwing in a little bit towards the end, a conversation about what we can do at NextWaveSTEM to help you out with that particular challenge. Okay. So what's the situation? We alluded to a little bit, but we can pull some data out and get a better idea of our situation specifically and our situation more generally when we think about particularly here in the United States, because this is where the vast majority of our participants are from. These are where our students are. This is in large part a driving force in our goals and how we're evaluated. Before this pandemic, PISA, just about every year, Program for International Student Assessments, does a very broad spectrum assessment of different STEM measurables, including math and science literacy. And a great way for us to measure trajectories is thinking longitudinally over time about how these different student populations move, how these different assessment metrics move. It's not perfect by any stretch of the imagination, but it gives us this broad idea that allows us to have a sense of what's happening really specifically with our students' identities when it comes, in this case, particularly the science. Math is kind of a different story. We didn't pull out that data for this. We could, but we want to focus on science literacy. The latest available data that was published back in May for in the international literacy scores from the program from International Student Assessment puts the United States as 19th out of 54 participating countries and or political areas, which is not bad. It is a slight improvement from that score that was last reported from 2015. So that 502, once again, is not terrible. But for those of us who live here in the United States, that number might also be a little bit alarming, especially if you think about the globalized scale in which we find some of our problems. Right now, the United States is neck in neck with some other industrializing nations with respect to carbon emission. That used to not be the case for many, many decades. The United States was the leader in global carbon emissions. That has changed. What has also changed is the current acute situation with regard to COVID. We are leading with respect to transmissions and cases reported daily. So we have some major global crises that need to be addressed and will require technological solutions. But in order to address those problems, we also need to recognize the really poignant importance of growing our technical acumen as well. Some uh, rising ships, some rising tides will float all ships, as they say. Other things need to be dealt with a workforce that we know is going to be available in the future. So that becomes even more critical that we continue to work to develop that talent. Um, and that is really reflected in this New York Times article from just last month. Pandemic has accelerated demand for a more skilled workforce, and a more skilled workforce is working in skills that are in the digital space. We're seeing a shift that may be a shift over a large amount of time towards having workers who are able to work technically, able to work remotely as well, and they're able to be responsible and effective digital citizens in space, in digital spaces. Well, not outer space, eventually outer space, but right now in digital space, which exists here in the US and all over the world. Um, Recognizing the changes in not only globalized problems, but real economic incentives and opportunities is going to be key, key, key. I say that 3 times because it's that important. Going to be so vital in creating a successful future for our students. So with that really hopefully poignant message there about why we want to continue to invest in science education, continue to invest in STEM education, I want to take just a little bit of time to talk about the next generation science standards. It's useful for those of us who may not be that familiar with them to get a sense of what they are, what they do, and actually how they change, because that allows us to make some planning with regards to emerging technology that we might use across age bands. There's no reason for us to think that an investment in a technology is meant for only a very specific subset of students. We can use it across a large breadth of our student population, which really returns that much more for our investment. So rewind back to the very nascent 2000s, the National Research Council in earnest launches a project to really revitalize science standards across the country. For a long time, science standards were kind of the Wild West. We had some national efforts to try to make a difference when we think of something like No Child Left Behind. But NRC did some really great work, and in 2012, 2013, Framework for K-12 Science Education is released. And when that's released, what it does is it codifies core ideas in science subject matter that students should learn in order to be competent when we think about the goal of science, which is inquiry into the natural world and natural phenomena. Um, it also lays out some really important science and engineering principles, not only the what, but the how. Our processes and mechanisms, those fundamental parts. So you see the skills development that is being built and what students need to know in order to be effective in the sciences. And then we also see this idea of cross-cutting concepts. No longer are we in the space where we think science should live in the silo where it doesn't affect other core materials. There is no reason why what your students are learning in science class doesn't reinforce what's happening in their mathematics education, doesn't reinforce what's happening in their English and literacy education, and vice versa. The cross-cutting concepts to Common Core math and Common Core reading state standards becomes really, really important when we think about what we can build using the next generation science standards. So we're building inquiry, we're building skills, and we're building the actual stuff, the substance of what our students need to know to be able to solve some problems and learn more about the natural world. These things really get defined in a useful way, in a very organized way, with regard to the framework for K-12 education back in 2012 and 2013. And it's from that framework that the NGSS standards are written. So broad spectrum, what do the standards cover? What are focuses for the standards? When we think about national next generation science standards, it is useful and to not think about specific subject matter areas, but a focus on um, the essence of what's happening in our broad grade strata, the elementary, the middle school, and the science. We see grade level specific standards in NGSS, K through 5, and then we get into more broad grade stratification in middle and high school, which is on purpose because there's a little bit of a flip. So when we think about our four DCIs, those core areas uh, for the elementary level, you'll see division into physical sciences, earth and space, going into life sciences, and then engineering, technology, and the application of science. This idea of the tools that we use and what they can be used for. When we think about what we're really trying to accomplish at the elementary level, we're empowering our teachers, our students, to answer some core questions. So if you think about something at the kindergarten level, it might be getting them to answer the question, what happens if you push or pull an object harder? Really dealing with physical sciences and this basic understanding of forces, which becomes really fundamental and key to a bunch of other disciplines throughout the course of their academic careers. But thinking a little bit more robustly, students will grow in their abilities. So at the third grade level, they may be tasked with answering the question, what happens to organisms when their environment changes? We're pulling in these ideas in Earth and space, but also life sciences. So we'll start to integrate across these DCIs, and we'll also grow taxonomically when we think about the student's ability to not only comprehend information, but to analyze information and make really, really reasonable conjectures. At the middle school level, we see a new strata that's introduced with regards to engineering design. We still have the physical sciences, life in earth and space, but engineering design shifts things significantly because instead of building this understanding of what technology can do, they make this pronounced shift to actually solving problems themselves, considering the information that they've taken in about the technology and then building solutions themselves through a process. Uh, so of course you may get a question like, what are the characteristic properties of waves and how can they be used. We're building in those physical sciences and also earth sciences when you think about the context of what a wave actually is. But then we grow even more because we're thinking about usage. Used by who? Used for what? Solving what problem? The consideration of the engineering process where they have to ideate, build, and iterate on a design becomes extremely paramount and really opens up a student paradigm. And at the high school level, we continue to build on those ideas and build on those skills in the physicals, life sciences, and earth and space sciences, but engineering designs as well. So we might have a question that is taxonomically even more rigorous. How and why do organisms interact with their environment? And what are the effects of these interactions? Builds in some really, really robust thought processes, especially if students consider human beings as part of those organisms. So we see of course, the rigor grow over time, but we also see this increased focus in the engineering design process, which makes absolute sense because it will be critical for our students to build real world problem solving skills, which is the whole point of the engineering design process. We have done webinars in the past specifically about engineering design, especially in the context of 3D printing. That's something I certainly encourage everyone to check us out on YouTube. I might drop a link to our YouTube channel in our chat a little bit later on. But you can see how we're growing here from not just understanding information in core subject matter areas, but then learning how to use that information more effectively, which is pretty much what the slide said. I got a little bit ahead of myself. The goal is to take that information that we're building on K through 5 and K through 8. We're also opening up some really robust opportunities in the project-based learning scenarios. The engineering design process is almost tailor-made for PBL experiences. I'm not going to dig too much into that today. We encourage you to check out our other webinars that have talked about PBL with emerging technology. But now we're really shifting the entire paradigm in what we are doing. The goal is to change from the idea of how is this done? How are other people doing it? How have people done it in the, how are people doing it, or how have they done it in the past? To how can you do it? Recognizing a problem and then putting a solution into actual practice. So now that we have kind of laid the foundation, we can jump into the broader idea for NGSS and emerging technologies, looking at some specific examples. Mary seems to have a pretty decent comment here, a good comment. Transition throughout K through 12. I had kindergartners testing good and bad baddies with a voltmeter. Have taught 6 to 10-year-olds jump drawer robotics. They also assembled Arduino robotics with parents' help in some school environments. Absolutely. A large part of the root of engineering is the ability to be clever, to take the information that we learned about natural phenomena, our hard sciences, combine that with mathematics and technology and solve some problems. So we're building in cleverness when we think about the actual instances of play that we can do, which really isn't so much baked into the NGSS, but when we think about engineering, playfulness and fun is very, very important. When we think about some of the most important and most robust engineering solutions that we've ever found, this idea of using the things that we have available to us in new and unexpected ways, even if that's to arbitrarily create solutions that we need to solve out of the junk drawer, is the stuff of genius. You will see children do things that we have never imagined them to do, and our children are already naturally ingenious. I am not a parent, but I have heard stories and seen small children see that cookie on the countertop and construct all kinds of manners of structure precarious, unsafe, dangerous books, chairs, fans to be able to reach that cookie. Our students are naturally clever. We just need to make sure that we bring a level of robust study so that we are not leaving them any blind spots or as little blind spots as we can. So I love this idea of drawer robotics. Really great comment there, Mary. So now let's make a little bit of a shift and talk about emerging technologies for the next generation science standards. And the great question there is where to begin? Well, I come back to the slide very often because it's fundamental and it's something that is evergreen. Um, Start by thinking through your learning objectives. And in order to think through your learning objectives, you should absolutely be collaborating outside of your particular department and or subject matter area. The best kind of learning that's going to happen for your students with regard to emerging technologies are emerging technologies that will connect to things that they're doing in other courses, especially in the context of doing hybrid learning. We don't want to put our students in situations where they either have really different expectations about how they're going to move through their instructions and what that's going to look like even logistically for students. That creates a really jarring cognitive experience and it actually disrupts focus. So building those expectations across your staff is really important. But also when we think about subject matter area, it becomes a way to engage students along different learning methodologies. A lot of our students are, frankly, really tired, just cognitively and physically tired. And many of us as instructors are cognitively and physically tired of doing the exact same thing in virtual instruction over the last few months. That is having our students work through what they have available through the LMS, which is generally form filled in on worksheets, transitioning them through some of our live instruction and feedback, transitioning them to prepared materials in video, and then the outward research work that goes into the product, a lot of that in reading and literature and mathematics, focusing on those core areas. That is starting to wear not only our students down, but us down as instructors. So what we have then is the opportunity to leverage technologies, especially in hands-on scenarios, where our students are going to be able to augment their learning in their core subject areas and while building their learning in their STEM areas as well. That becomes a very useful way to make the subject matter stick in both areas. Is really critical. So with that being said, let's think about drones and 3D printing. And the reason why I keep coming back to this, if you've been in NextWaveSTEM webinars before, we love talking specifically about drones and 3D printing. We offer course material in computers, in AI, computer science, and in robotics as well. But the reason why we love working in the drones and 3D printing space is because these technologies in particular offer the ability for our students to work remotely and virtually in simulation and also hands-on, both in situations where they might be working at school and working at home. If we can think a little bit out of the box, we can make the materials, the physical material available for the students in such a way that that hands-on learning becomes a real and robust thing they can do. It's just not relegated to the school, it's something that they can do. So when we think about drones, students will be, of course, engaged in computer science when they're making these drones fly autonomously. We're not talking about flying a drone with a control stick. We're talking about putting in computer code, pressing a button, and letting the drone work while we do other work independent from the drone. That also builds in these ideas in mathematics because we're going to need to mathematically define how the drone moves through a three-dimensional world. And as we're solving these problems, we're working through engineering principles. So we're programming, we're simulating flights and using actual flight. We are using um, actual use case scenarios to build and construct our programs to build our solutions that we can physically test. Um, and then when we think about 3D printing, this becomes even more robust and actually directly on point with our current situation when we think about COVID and our 3D printing courses and with 3D printing, again, we're building in skills, computer aided design skills. So we also are involving the art space here, but also really, really robust engineering design because with 3D printing, we have the awesome opportunity to engage our students with product design. Many of us who are career technical education instructors who may be doing some industrial product design or some general product design, even architecture in that space, are going to be able to use the 3D printer in some really, really robust ways. Um, so we're really working through ways for our students to do cloud-based design. As long as they have a computer, IO or Mac OS, Windows or Chromebook, and a persistent internet connection, they'll be able to design. They'll be able to work through the steps of the engineering design process, and we can engage either remote printing services or with the time that they're able to spend in the class, engage with the physical printer that you might have in your classroom. And the great thing about the physical printer is that doesn't have to be something that just lives in your classroom. We can empower your students so that they can use those or have access to those printers at home. So these are our two bedrock technologies, things that we can do both remotely and in person in our instruction that we can now leverage using the next generation of science standards as well. So let's take a look at some of those standards. And let's begin with drones. Some examples of things that are happening here. Um, and this is where we get a little bit interactive. So we have three standards that I've pulled out that we've used in NextWaveSTEM training and materials previously that we try to do alignment for. And when we think about these standards examples, we're thinking about the assessment opportunities. We all know that's how our standards work. The standards are there for us to build something that we can assess to. And we may or may not understand the technology a little bit, but we want to talk about ways in which we can use the technology to assess these situations. So we've got three examples of standards. One from the middle school level 3 through 5, another from the, one from the elementary level 3 through 5, another from the middle school 6 through 8, and another for the high school 9 through 12. Um, the first standard deals with motion and stability, forces and interactions. Plan and then conduct an investigation to provide evidence of the effects of balanced and unbalanced forces on the motion of an object. For the middle school, we have on an engineering design standard, analyze data from tests to determine similarities and differences among several design solutions to identify the best characteristics of each that can be combined into a new solution to better meet the criteria for success. And then our high school standard deals with biological evolution. Create or revise a simulation to test a solution to mitigate adverse effects of and adverse impacts of human activity on biodiversity. I'm actually going to quiet down a little bit myself and encourage you to maybe pick a standard or multiple standards. You don't have to share which standard you're picking, but I would love to know what are some of the performance tasks, what are some of the accessible moments that you might build into a lesson using drones for some of these standards. And I got a question here from Mary, a really good question. Do these standards coincide with the ISTE standards? They can. Many of them are directly overlapping with ISTE standards as well. In our NextWaveSTEM material, actually, we do define ISTE as well as next generation science standards with regard to lesson alignment. We focus on NGSS because many educators focus on those more often. So really good question there, Mary. So I'll just give us a minute and let you consider and maybe bring in a little bit. If you were doing a drone lesson and you were thinking about an assessment opportunity, think something for your student to do, what might they do to meet maybe one or multiple standards? And I will actually time myself. I'm going to give myself 60 seconds of silence while we chime in on the chat. And there is no such thing as a bad answer. So we're a little quiet here on the Western Front, but that is just fine because it doesn't have to be super robust for us to think about what we might do. Um, and we can kind of go from the top if we understand what the standards are trying to pull out of the students. For 3 through 5 standards, dealing with emotion and stability, they're looking for an investigation to provide evidence of the effects of balanced and unbalanced forces on the motion of an object. If we imagine our drone hovering in the air, we've created a system that is in balance if we understand our forces. There's the force of gravity pulling down on the drone. We have the force of gravity pushing up on the drone. Um, the situation in that situation, we have an object that is balanced. And so it's not moving. That drone standing steady in space is a balanced scenario. And at any point we cause the drone to move, we've actually changed the forces operating on the drone. That could be as simple as you slightly pushing the drone and causing the drone to drift. That could be even more intentional with you programming the drone to move and observing the way in which the rotors, the actual propellers on the drone, change their motion. So we have that forces and interactions that we can investigate, um, observing, recording what we observe about the drone. And when we think about the 6 through 8 engineering design situation, we find that we're being asked to identify the characteristics of different design solutions. If that is programming a drone to deliver a pencil or deliver a toilet paper or deliver your next package from Amazon, simulating that delivery means that our students are actually going to drop in pieces of code and evaluate whose code is more accurate with the delivery, whose code takes into account different obstacles in an area, whose code will actually return the drone back to from where the drone came or go on to the next delivery. We get to create these criteria for success, and then we can evaluate our students based on those. And then at the high school level, a great simulation for the ways in which we might mitigate the adverse impacts of human activity and biodiversity is thinking about drones as a replacement for something that's being destroyed by human activity. I don't like bee stings, but I love bees. I love bees because I like food. And if we've paid attention to science news in the last couple of years, we've learned more and more about hive or colony collapse syndrome, a disease that is killing literally millions of honeybees all across the United States and making life more difficult for many agricultural sectors, changing the prices of food, but that is also a direct result of changes in biodiversity because of human activity, things like global warming and air pollution. Could we design a scenario where pollination is done by drone, simulate, or even test that? That becomes a really useful activity for our students going into an a situation where we're thinking about that standard specifically. No, it's kind of heady, but let's try a different one. Let's think about 3D printing. And the same idea here applies when we think about ways in which we can engage standards for our learners. So we've got 3 standards once again. One standard pulled from the elementary level, another at the middle school, and one at the high school level. The difference here is that all of these standards are engineering design standards. If you ask me for a technology that you could use to satisfy engineering design standards, I could not have imagined a better technology than 3D printers. For those of us who've ever done any kind of 3D printing before, we know it's a little bit of a process, but we can whittle that process down really into 3 steps. The first being the actual design of the piece or pieces that we want 3D printed. That part where we're not worried about what the machine is doing at all. We're just worried about whether or not we can adequately and accurately create this object in digital space before we ever do anything with the machine. The second part of that process we think about is slicing. Can we effectively take the digital data of our design and translate that into instructions that our machine can actually follow and understand? And then the third part of that is the actual printing, where we take the plastic filament or the resin or the powder, whatever the medium is for 3D printing, and translate that into a physical object. Once again, this is really on point right now when we think about the ways in which schools and businesses and companies, and maybe even some of your schools, some of your nonprofit organizations, use the 3D printers that they had available to them to produce personal protective equipment. That becomes a really useful way to make this learning real for your students. To say that, okay, we're solving this real problem, and this real problem is affecting us right now. It may be the very reason why we're looking and talking to you over a computer screen as opposed to in this classroom. So we can use these standards to make that real. And we might even focus on that a little bit. So for the 3 through 5 engineering standard, we're being asked, or students are being asked, to generate and compare multiple possible solutions to a problem based on how well each is likely to meet the criteria and constraints of that problem. Our middle school standard is engineering design as well, where we are to develop a model and generate data for iterative testing. Testing that just doesn't happen once, but happens after small changes. And not only iterative testing, but modification of a proposed object, tool, or process such that an optimal design can be achieved. That also becomes a really robust opportunity. We don't focus so much on processes there, but we could. And then that high school standard, uh, which is to evaluate a solution to a complex real world problem based on prioritized criteria and trade-offs. They account for a range of constraints, including costs, safety, reliability, aesthetics, as well as possible social, cultural, and environmental impacts. And we can jump right into these. If we are to generate and compare multiple possible solutions to a problem, um, once again, we get to decide what that problem is, and that problem can be extremely arbitrary. But the thing about that problem is because we get to decide it, we also bring to bear our prior knowledge of the subject matter area. A great example for our middle school students, 2 through 5, I might have them use my 3D printer or the school's 3D printer to design a doorstop. You may already have a doorstop, or you may have lost your doorstop at the end of last year and it's never to be seen ever again. It was your favorite doorstop. It kept your door locked open. It created an amazing cross breeze in that window in your classroom, but the doorstop is gone now. Someone else recognized its beauty and stole it from you. That 3D printer may be the catalyst in which students do their first basic design to solve a real problem for you. So that's where we actually analyze the criteria and constraints. How big is this doorstop allowed to be? How much material are they allowed to use in designing the doorstop? How well does it have to hold my door open? How much force am I allowed to put on the door of the doorstop before it gives way? And those doorstops are going to be different designs. They may have some things in common, but your students are going to get very creative with the kind of things that they're going to do with their 3D printer to create a doorstop. If we think about the middle school level, our goal there is to think about iterative testing through a proposed object, tool, or process. What kind of thing are the students going to design and print and then retest and retry over and over again? This also gets to be arbitrary. You get to decide this as an instructor. So for you, iterative design, something that you know needs to change and get a little bit better over and over and over again, can be as mundane or as complicated as you like it to be. And sometimes our students actually will give us the ideas for this when we survey them. I've had students in the classroom tell me that their lockers are too small. So they will actually use their 3D printing acumen, their design skills, and their ability to actually test with their physical lockers, building parts and pieces that can slide and fit into their lockers that make it easier for them to subdivide and keep their lockers more organized. Because they can't expand upon the physical space in their locker, they might need to use the space in the locker to be more organized. And the 3D printer becomes a actual tool that allows them to explore ways to get that done. But when we think about the high school level, we are dealing with an actual complex real world problem that we can prioritize and consider constraints. And for that, we will highly suggest even the course that we did on designing PPE. How can we design objects that help people not transmit a virus? Um, how much will those objects cost to produce using our 3D printer? Is there a way to produce them and use less money? How effective are they? What have you learned from other products that have been produced using a 3D printer? Is it something that I actually want to carry and brings me joy when I look at it aesthetically? Do we need to think about what this object might come to symbolize culturally, socially? What happens when this object is done? Will it biodegrade? Will it end up in a landfill? All of these things become considerations and really robust learning opportunities for our students as they work through 3D printing as well. So I know I said a mouthful. We crammed a whole lot into a little bit of time. This is the opportunity where I talk about another housekeeping note, which is that if you missed it, if I'm going way too fast, if this got boring, or if you were just riveted and all in and had some ideas for things that you want to pull out, don't worry about the notes that I'm sure you're furiously scribbling all over your notepad. We will also be providing copies of the slide deck from today's webinar and the recording from today's webinar. The recording will be sending to you directly, and you will be able to find it later searching for NextWaveSTEM webinars on YouTube. So don't worry, you haven't lost anything yet. But finally, I should say, we want to talk a little bit about how NextWaveSTEM can help your specific situation when it comes to meeting those standards, and how we can do that with courses that are both virtual and in-person ready, hybrid friendly courses. The first way that we're going to continue to support, we're committed to, is our webinar series. You've already seen this page. You're here today. You registered for our webinar. We're encouraging you. Share this information with your colleagues as well. Next week's webinar deals with practical STEM applications that can be implemented in the class today. Some of us are going to be going to full live instruction and are looking for ways, now that we are reoriented into the fall and what we want to accomplish, to integrate STEM in some really concrete ways. We'll be talking about that next week. And we've got a slate of webinars that we will be continuing for the foreseeable future. But we are also, as I mentioned earlier, making resources available to schools. That means that NextWaveSTEM is right now licensing our curricula. Curricula is K through 12 and drones, robotics, 3D printing, and AIs and artificial intelligence, which deals with computer science. These courses can be hands-on as well as virtual, and they are hybrid ready. We can be the all-in-one solution that you need. That means that you'll have access to the curricula. I will be available to train you personally, remotely. And we also are making sure that you have access to all the equipment that you may need, whether that's 3D printers, robots, drones, whatever your situation, we want to make sure that you have exactly what you need to be successful. And on the other side of that coin, if what you need is an instructor, NextWaveSTEM offers instruction as well. Our team of instructors is certified. They are STEM professionals and educators themselves, conducting live courses if you're in the Chicagoland area. And if you're a little bit further out, we are doing virtual instruction as well. So if you're in need of certified instruction in your out of school time courses or even your in school time courses, NextWaveSTEM is available to help you with that. And finally, be ready. Be ready for the fall. Um, that means that you want to make sure that your curricula is ready for the hybrid learning. Definitely encouraging you all, and we've seen this more and more across the country, to continue to avail yourself of those professional development opportunities that will build your skill set in hybrid teaching. It's unfair. It really is that so many of us are in situations where we'll have to learn a new paradigm at the drop of a hat and try to make it successful with our students. I know us, I know teachers, we love our students and we are going to try to make this thing work. So continue to press forward, work and get some good rest as you are thinking through your standards alignment, as you're building your school culture, as you're building your logistics, as you're just learning how to work Google Classroom and how not to look crazy on Zoom. We believe in you and we want to encourage you to continue to build your skills. So that is a lot of information that was said there. I want to open it up now. Are there any questions? Questions about standards, questions about things that you might do with emerging technologies, whether that's drones with 3D printing or other emerging technologies? Or do you have other really good suggestions about what you would like to see with regards to emerging technologies helping to meet standards? The floor is open to you. I'm going to be quiet while you type away. Mary had a really good one here. Makerspace creations. Yes, Makerspace becomes a really interesting opportunity because it really leans in a robust way into the idea of a longitudinal project-based learning. It gets out of this paradigm where traditionally we give students instruction and rote work, instruction, rote work, instruction, rote work, instruction, rote work, hoping to reinforce that instruction, and then hit with some kind of summative assessment at the end. And then we have some kind of project kind of as a dessert or a cherry on top. Makerspaces combine multiple technologies. And then the multiple technologies will feed across other core areas. So this makes it a really, really useful place to build in a lot of core areas and STEM subject matter all together. What does that look like? Your makerspace may have a 3D printer, may have a laser cutter, may have a laminator. Your makerspace now has lots of tools to allow your students to build and sell a product. And you may now combine some things happening in your CTE space, or maybe if your school is advanced and has business and marketing offered in some of their high school curricula, now becomes a place where you're taking the manufacturing and the marketing and building an entrepreneurship. Ideas in economics and math, both micro and macroeconomic, fused together with the whole engineering design process. And through this entire cycle now, we've pulled together 5, 6, 7 different core subject matter areas into learning that we can do. And kind of our makerspace becomes a linchpin. So if it's using my woodcutter to create a box, using my 3D printer to make a custom label on this box, or a custom support, or maybe changes a specific hinge on the box, that becomes a learning experience. And it goes that much even further, because in the ways in which we empower students with these particular technologies, who's to say that hinge is something we've never seen before, hasn't been patented, and maybe we have a student at our school who has a patent in high school. That is a tremendous opportunity in which makerspaces give us these new affordances. So we can pull all of these seemingly disparate ideas into one space. Um, love this idea of makerspaces. And makerspaces, I think of being as really robust manufacturing spaces. Laser cutters, CNC machines, uh, the traditional 3D printers that we use that are fusion form molding, or even the resin ones, become great resources for makerspaces. And we love talking makerspaces here at NextWaveSTEM. We could talk about those all day long. Great question there, Mary. Are there any other really good questions? We've got a few minutes left. Well, just in case, I don't think we have any more questions. I know that we've got quite a bit to digest, but just in case you do happen to have any more questions, that is me. My name is Desmond Martin once again. That's my email, very easy to find, desmond@nextwavestem.com. We're also available on most social media platforms, Twitter, Instagram, LinkedIn, and Facebook. We are not on TikTok, but we may be one day soon. I love questions. I love seemingly random questions. I love questions that are not so random and really specific. We can dig in and jump into the weeds together with you. Or if you just like to get connected to someone as a part of our school partnerships team, we can also point you in the right direction. But for all of you who were able to take a little bit of time out of your day to join us, we are so grateful for the time that you spent. We do hope that you found it helpful. And in the meantime, once again, be on the lookout for that follow-up email. The follow-up email will include the certificate of participation for today's webinar. It will also include a copy of the slide deck and also the link to the recording for today's webinar. So we're hoping that you have all the materials that you need to get started on the right track. That being said, we will love to see you next Tuesday or next webinar. But if we can't, until the next time we do see you, hope that you all stay safe, that you have fun teaching STEM, and that you have an amazing rest of your day. We'll be talking to you all soon. Thanks a lot.